Welcome to ToKCast, episode 7 on the nature of science, where we're going to look at what science is and what makes it special. In the last episode, I spent a long time, perhaps too long, in explaining exactly what science is not. When I use the word science here, I mean what the TOC guide refers to as the natural sciences. For now, when you hear me use the word science, presume I'm talking about the natural sciences. And in this sense, science is not a process where predictions are generalized from repeated observations. That is, science has nothing to do with the fallacious method of reasoning which is commonly called induction. Unfortunately, this is the view you will read and hear about at various times when studying TOC. Now, I claimed that the process of induction not only did not explain how scientific theories are justified, but also that induction wasn't even a method of justification at all, plain and simple. It does not even work for everyday justification of our theories. What I have done then is dismiss the entire problem of induction by saying that no knowledge can ever be produced through induction. It's an unfortunate and rather serious shortcoming of texts and resources that choose to characterize science in this way. Science is, after all, our best attempt at trying to understand the world. It is not a mere generalization of predictions. Once again, I urge you to research and consider alternative points of view to my own. I'm happy to discuss these. But science is a process, just not an inductive process. It's a process that begins with a problem, offers testable solutions, and generates explanations which are themselves predictive. We can define science, therefore, as a process for creating new knowledge, as well as the body of knowledge generated by that same process. So on this view, science generates reliable theories about how the world works. The best theories we have in this regard, at the moment, form the body of scientific knowledge. Now, just as an aside here, I've used the word world a number of times in these podcasts, and I'm using it in the philosophical, not the geographic sense. In other words, it's bigger than just the planet Earth. The world, in philosophy, is everything that exists. It's the whole universe, and to some extent even more than just the physical universe. It's the sum total of reality. So when I say science is a process, and a collection of our best theories about how the world works, I use the word theory in a special way that I've alluded to before. A scientific theory, above all else, is an explanation. Our scientific theories are our best explanations of everything that exists in the universe. But what is an explanation? An explanation tells you why something happens. It gives reasons. An explanation allows you to understand a process or a system. It is also a representation of a process or a system which closely resembles, in some sense, that process or system. For example, the theory of how stars produce light consists of symbols we call words, and mathematics that represent in symbolic form this process. Between the star itself and the explanation, there is some sort of correspondence between individual components of what is happening in the star and the symbols in the explanation. Now, before the scientific revolution, which happened in the wider context of the Enlightenment, centered on Europe in the 18th century, people thought that most reliable knowledge came from authority and tradition. An authority would generally rely upon either some rule of thumb or perhaps an ancient text. The physics and astronomy of Aristotle was followed because of tradition. Indeed, Galileo is reported to have remarked that few of his peers wanted to look through his telescope because most everything that needed knowing came from ancient texts and scholars. Clearly, if Aristotle taught that the geocentric theory was what natural law mandated, what could the telescope add or subtract from this? The Church, as is famously now known, used its authority to enforce belief in Aristotle's physics. The Bible itself is not entirely clear on the question about whether the solar system is geocentric or heliocentric. taking another historical example. If, say, your problem was a medical one, like, say, some infection, then a frequent treatment that came from traditional medicine was bloodletting. The idea here was that letting the supposedly disease-carrying blood out would do some good. Now, of course, we do not rely upon authority or tradition to validate our knowledge claims today. Indeed, the foremost scientific organisation in the world in 1660 was the Royal Society of London. Their motto was, and remains, nullius in verbia. Take no one's word for it. Insofar as these days authority or tradition do have any part to play with knowledge claims, we understand the liabilities associated with trusting these sources. Now, I might have to take it on authority to some extent that Andrew Wiles' 100-plus page-long proof of Fermat's last theorem is valid, because I cannot understand the details, or that the best treatment for a cerebral aneurysm is endovascular coiling, because I've not had training in neurosurgery. But I also know that these things can be checked by people who do know, and that anyone with sufficient time and intelligence can check the relevant facts. Ultimately, such knowledge does not spring from authority alone. It springs from scientific or mathematical investigation into the world. These investigations lead to problems. How is it that we explain the origin of species? How do we explain how people catch diseases? How is it that metals corrode? Why do planets wander across the night sky? And what is the cause of earthquakes? These problems demand solutions. What is noticeable about all of the solutions to these problems is that we explain what we do see in terms of something we cannot see. Take all the different animal species in the world, something we can see, explained in terms of gradual evolution by natural selection over many eons, something we cannot see. Sick people, something we see, explained through germs and viruses, something unseen. Corrosion, planetary motion, and stars, all seen, explained through electron transfer, the curvature of space, and nuclear fusion, all unseen. Science makes conjectures about these unseen entities to explain these processes. We do not observe these entities directly. We do not see evolution by natural selection occurring. We do not see the laws of physics or nuclear fusion. Indeed, to be very strict, we do not even directly see anything. When we look at one type of finch and notice it is different to another, we do not see a finch as it is. What happens is that light enters our eyes and an electrical signal is sent to our brains. This electrical signal is a pattern of impulses along neurons in our brains. One pattern of impulses rather than another means that we recognize a finch as a red finch rather than a blue finch. Our brains interpret these electrical impulses in such a way that we experience the world in the way we do. Our brains synthesize the pattern of electrical activity sent to it by our sense organs and form it into a coherent whole that forms our conscious experience of the world. How is it that our senses give us knowledge of the world? Well, when it comes to seeing, it's just the way I've described. But notice that understanding this way of knowing relies upon a scientific theory about sense perception. This scientific theory involves explaining how light is reflected from the wings of finches and how light is then refracted by our eyes, and ultimately how it causes electrical impulses in our brains that allow us to say that our senses give us knowledge about the world. This is just what I said about how sense perception works in episode 3 of ToKCast. We do not observe the world directly, to be sure, but I emphasize again that this is no real problem for anyone who is not interested in certain knowledge, but rather who is more concerned about explanations. Our scientific theories about how our senses work explain that they represent the world to us in such a way that we can gain reliable information about the world. And the reliable information they give us about the world, however subject to error that information might be, is useful for developing theories about the world. The consequence for science on this view is simple. We never directly observe anything. So observation is not the most important thing in science. So what's the most important thing in science then? Well, I'm glad you asked. It's explanation. And explanations can be good or bad, as I said in the last episode. Those explanations produce predictions, and those predictions can be tested against the observations. If the predictions do not match the observations, then we must change or reject our theory. But there is more to a good theory than just this. It must also be based upon few assumptions. And this is Occam's razor. Occam's razor is also sometimes known as the principle of parsimony. And although the two ideas are different in very subtle ways, I will use them interchangeably here. Occam's razor says, in common language, all else being equal, the most simple theory is the preferred one. Now, I prefer to say that Occam's razor can be expressed as the theory which makes the fewest assumptions is to be the preferred one. Now, it's important to notice here that Occam's razor is also not the most important concern in choosing the best scientific theory. The best scientific theory must also explain as much or more than all of its rivals, in addition, of course, to being falsifiable. Occam's razor is just one of the features that a scientific theory must satisfy, but sometimes it can make all the difference. The reason why Copernicus first proposed a heliocentric theory was because Ptolemy's idea of a geocentric theory required far too many assumptions. In order for the predictions about the behaviour of planets to be accurate, epicycle upon epicycle had to be independently assumed. It was much easier simply to assume that the Sun was at the centre. At first, the predictions that the heliocentric theory made were actually not as accurate as the geocentric theory. But as we can see from this example, sometimes predictions are not what matter most. It is both Occam's razor and the ability to make precise and accurate predictions that, taken together, constitute important features of a scientific theory. But there is yet another feature now to add to these two features discussed so far about scientific theories being predictive or falsifiable and able to satisfy Occam's razor. The next feature is that scientific theories should also be hard to vary. They should not be easy to change. An example might help here. Why is it that earthquakes sometimes happen in Japan? An actual explanation provided by the Japanese themselves in ancient times involved a catfish, a huge catfish. This huge catfish was called Namazu. Namazu lives in the mud beneath the earth and is guarded by the god Kashima, who restrains the fish with a stone which is put over his head. When Kashima lets his guard fall, Namazu thrashes about, causing violent earthquakes. Okay. So what's wrong with this explanation? First and foremost, it is easy to vary. Why a catfish? Why not a tuna? Or a lizard? And why the god Kashima? Why is a rock needed? Why wasn't the catfish tied up? This explanation is easy to vary, and it postulates a raft of unsupported entities which themselves require explanation. It is hardly parsimonious. It does not obey Occam's razor. Rather than actually explaining earthquakes, it simply postulates a bunch of needless assumptions about gods and catfish and rocks, each of which themselves would require explanation if we really were serious about trying to solve the problem of what causes earthquakes in Japan. And this explanation does not generate anything in the way of accurate predictions. Is this theory even falsifiable? Well, actually, in a sense it is. If the ancient Japanese who believed this theory knew about, say, the United States, which is far from Japan, and they further knew that the United States also suffered earthquakes, then how would Namazu explain earthquakes there? Presumably, such an observation of earthquakes in the United States would, strictly speaking, falsify the theory about Namazu. If the islands of Japan alone are on the back of the catfish, then what about the United States? It's far larger than Japan. Presumably, it would require many catfish, or perhaps it requires something larger like salmon. So it's not the fact that the catfish theory of earthquakes isn't falsifiable that makes it unscientific. It's probably falsifiable. It's not scientific because the theory is too easy to change. We can substitute catfish for anything you like. And also, those entities which supposedly do the explaining, the god and the catfish and the rock, actually do nothing of the sort. They complicate matters by themselves being unexplained, so they violate Occam's razor. The theory is not simple, it's complicated. It postulates a raft of things, all of which are unexplained. You're in a worse mess than before you started trying to explain anything. We really are none the wiser. And now we've got a raft of strange entities, including gods, catfish, islands attached to the vertebrae of catfish, stones used to restrain imprisoned catfish, questions about feeding and motivation, and the list is long and preposterous. It's certainly fun to make up such theories. We could make up one now. In the centre of the earth live giant trolls. The giant trolls push boulders around just below the surface of the earth. These boulders act like bearings between the surface of the earth and layers of rock deeper down. Now and again, one of the trolls, Gary, not as smart as the rest, lets go of his rock and it crashes into some of the other trolls. At these times, the collisions can be felt on the surface of the earth as earthquakes. This explains earthquakes. Again, we can go through the list of things wrong with this explanation. First and foremost, it is too easy to vary. Why trolls? Could I not simply change troll for something else, like say, giant rhinoceros? Couldn't I change boulders for huge wheels? So what is the actual theory which explains earthquakes in Japan? And how is it any better? Well, it's the theory of tectonic plates. Japan sits at the interface between two large solid plates that are moving at the rate fingernails grow and are grinding against one another. Pressure builds up and is released over time, and sometimes this happens quickly. This is felt as an earthquake. This also happens to explain why there are usually aftershocks, and also why, in and around this country, we find volcanoes. The gaps between plates are places where the material below the surface, which is molten, can break through the gaps. This also explains why the plates move. They are floating on this very molten stuff called the mantle, which we call lava when it comes to the surface. This explanation is shockingly hard to change. Could we simply change plate for anything else? Now, it has to have all the properties of a tectonic plate, and not introduce anything further that's unexplained. Okay, what about a big catfish that looks just like a plate? It does everything that a plate does, doesn't it? Yes, and more. It then complicates matters, as we would then want to know, how does this catfish eat? What does it eat? How, if it looks identical to a tectonic plate, can we reasonably assert that it is actually a catfish? The plate, like all aspects of the tectonic plate theory, are very hard to change, and the theory makes predictions. It says we should expect earthquakes all over the world, but especially where plates meet. We should further expect a pattern of volcanoes. They should be clustered around regions where plates meet also. It also predicts that we should find evidence in the geological record of the continents having moved over time. For example, we might find very similar rocks now on opposite sides of the Earth, or even similar fossils on countries that now have entirely different organisms living on them. It also fits well with the rest of what we know about science. In this case, the theory of tectonic plates fits with what we know about paleontology. Paleontology suggests that the continents used to be connected, as we know that the same dinosaurs that lived, for example, in South America, also roamed in Africa. This is only possible if continents can drift. I hope what I've showed here is that a scientific theory is an explanation. It's an explanation that could possibly be wrong, but so far has survived all attempts at proving it wrong. It should also be difficult to vary, and it should fit in well with everything else that we know about science. So let us summarize what we have learned so far about what it takes for a scientific theory to be good. Firstly, it should be able to make precise and accurate predictions. That is, it should be testable. The science of astronomy makes clear predictions about where the planets will be in the night sky. Next, it should rest on as few assumptions as possible. That is, it should conform to Occam's razor. All else being equal, it should be the simplest theory. Thirdly, it should be difficult to vary. Next, it should explain as much, preferably more, than all its rivals. It might not explain everything, but that's okay. The classical example is that Einstein's relativity explains everything that Newton's physics explains, but also it can account for some things that Newton cannot. For example, Einstein's relativity correctly explains how much starlight bends during a solar eclipse, and it also explains what is known as the precession of Mercury's orbit. That is, how much the axis of the orbit moves as Mercury goes around the Sun. And also, as far as scientific theories are concerned, in order for them to be good, they should mesh well with what we already know about the rest of science. The theory of evolution by natural selection does not contradict anything we know in any other area of science. Indeed, the theory that species change over time due to the natural selection is a non-random process, of mutations, these are the random part of evolution by natural selection of random mutations, this theory fits in perfectly well with what we know about genetics and physics at the molecular level. We know that genes exist on a molecule called DNA, and that these genes carry information that codes for certain features. The mutations which occur can be caused by a number of things, including radiation. If evolution by natural selection was contradicted by some law of physics or chemistry, then we would have reason to question it. It's worth mentioning, just as an aside here, that one objection raised by some about Darwinian natural selection is whether or not it contradicts what is known as the Second Law of Thermodynamics. It certainly does not. The second law talks about a certain property of closed systems called entropy. Entropy can very loosely be called disorder. The higher the entropy, the more disordered a system is. So, for example, ice is a nicely ordered crystal, but liquid water is disordered, with all the molecules all over the place, and far more free to move. The second law says that for a closed system, entropy must increase. Some people loosely also contrast the disorder of high entropy with the complexity of low entropy, and assert that evolution causes complexity and therefore order to increase, in contradiction to the second law. For example, evolution on Earth shows that natural selection is making the ordered, that is life, out of the disordered, i.e. non-living stuff. The important point here is that the second law applies only to a closed system, and the Earth is certainly not a closed system. Energy is constantly falling onto the Earth from the Sun. This energy from the Sun enables life to make order out of disorder, in complete agreement with the second law. Taken together, the Sun and Earth system, all as one, the total entropy of the system does increase. I mention this because if some people who claim that there was a contradiction were right, then evolution would indeed not mesh well with what we know about physics, and we would have to question one of these theories. As it actually is, however, both fit perfectly well together. You simply have to understand your thermodynamics more completely to see that there is no contradiction. Now we have 5 features of a good scientific theory. It should be falsifiable, that is, make predictions. It should rely on as few assumptions as possible. It should be hard to vary and explain more than its rivals, and also fit with everything we already know. Now, what else is there that science does well? Well, here is a 6th feature of science, generally speaking. It improves. That is, it makes progress. Science is a process of open-ended discovery. We do not reach a point and then say, well, now we're finished. No, we continue revising our theories. We continue to refine them and improve them. Things are objectively better now than in the past. If you have bacterial meningitis, the medical treatments available to you now are objectively better than they were 200 years ago, when the disease would have been a death sentence. If you wish to get from Sydney to London, we have superior ways of doing so now compared to any time in the past. Clearly, we have made progress over the centuries. Where once our only means of transportation was our feet, now we can fly. And we can fly because we really have learned some things about aerodynamics and internal combustion. If you wish to explain what those lights in the sky are now, then it can be said that we have made progress in the last few hundred years, and we continue to learn more. science improves. In this latter case, our knowledge of astronomy and cosmology is far from complete, but there is no question it is an improvement upon what we once knew. Indeed, the data comes in daily, and the scientific papers are relentless in coming. The steps sometimes falter, but this is no problem. The general trend is an improvement in our knowledge. We know there is more to know and more to explain. Our exploration of the cosmos is truly open-ended. Indeed, our attempts to explain all phenomena remain so. Yet we can still say some things with a high degree of reliability. We might not know everything about exactly how nuclear fusion in the core of stars works, but we know much more than we did 50 years ago, and we knew much more then than we did 200 years before that. This sense in which science admits of progress can be identified with Karl Popper's idea of verisimilitude.
What now?
Verisimilitude. It means closeness to truth. Now, it might very well be an axiom of epistemology that we can never know if we have ever described reality as it really is. That is, we may never know if we have obtained the truth about the world, but we can make objective claims about our theories compared to one another. Clearly, the heliocentric theory is closer to the truth than the geocentric theory. Anyone who denies this has probably ruled him or herself out of the discussion. It is not a problem that we do not know for certain what the truth is. As I have said a number of times now, almost like a mantra, a scientist is not interested in certainty, but rather in explanations. So long as we seek to maximize verisimilitude, closeness to truth, then we have achieved our aim in science. If our explanations map reality as closely as possible, our only gauge of this is to assess our theories as being better or not. I want to return for a moment to this important interaction between what the ToK guide refers to as a way of knowing, namely sense perception, and the area of knowledge called the natural sciences. I have said already that scientific theories explain the seen in terms of what is not seen, and what is not seen cannot come through the senses. I think this shows that sense perception as a way of knowing is only possible when coupled with reason. Now, empiricism is the idea that knowledge is gained through the senses alone. Clearly, such a view is not true. The laws of nature are mathematical in form, but we do not see mathematical equations. We do not see the curvature of space-time, and we do not see photons or the origin of species. So empiricism alone cannot be correct. As an aside here, it's worth noticing that induction also seems to assert that the unseen, for example the next sunrise, resembles the seen, for example the last sunrise. We've already seen that this is not true. Scientific knowledge can be tested by observation, but can't be derived from it. We never observe something as it is in itself. We do not see books, for example. We do not even see light. Our eyes detect light, but we are not our eyes. We are our brains. And our brains detect electrical impulses. And we do not detect those as they are. What they are is electricity. Instead, our brain interprets those impulses, those electrical impulses, and synthesizes them into a coherent whole that forms our consciousness of the world. And it is here, in our consciousness, that we can reason about our sense perceptions and form theories and criticize those theories as being good or bad explanations. But we never perceive reality as it is. At least, we do not know if we perceive reality as it is. Rather, we reason about the contents of our mind and seek to explain what it is we perceive. Our best systematic attempt at doing this is known as science. Next time, I want to address exactly what the scientific method is and some more of the questions from the guide about the area of knowledge we call the natural sciences.
For resources and links associated with ToKCast, visit the ToKCast website at www.tokcast.net.